While watching the window washer on a ladder, Einstein thought about what would happen if the window washer fell. For most people, imagining this would just conjure up disturbing images of the poor guy landing on the ground below, and the story would not have a happy ending. Einstein thought about it differently. He put himself in the window washer's perspective and imagined not what would happen when he met the ground, but what he would experience as he was falling. What he realized was that if he was falling, gravity would be the only force acting on him. He would be accelerating towards the ground, but since the ground would not be pushing up against his body, he would feel no weight. With no wind resistance, he would be in free fall, and this would be no different than being weightless in space. In a way, gravity and acceleration were different ways to describe the same thing. This is where Einstein had a huge insight. The way to connect gravity with the theory of relativity was through the idea of acceleration, since the two are equivalent. Einstein imagined being in a room with no windows. And if the room had a bathroom scale handy, what would happen if you stepped on the scale? Well, if anywhere stationary on Earth, you would weigh 80 kilograms, or whatever your weight is. Now he imagined being in the same room in space. Now what if the room was on a spaceship that was accelerating in an upward direction at 9.8 meters per second, which happens to be the exact same as the gravitational acceleration on Earth. What would happen when he stepped on the scale then? Well, the scale would read 80 kilograms, just like it did on Earth. The acceleration on the spaceship would appear to him inside the room as being indistinguishable from being stationary on Earth. If he didn't know he was on a spaceship, he could just as well presume he was on Earth. There would be no way to tell the difference. Or would there? Einstein thought about this and asked himself if there was a way to tell the difference. He imagined what would happen if he took a flashlight or a laser beam and pointed it from one side of the room to the other as the spaceship was accelerating upwards. If he had a sensitive measuring instrument, he could measure the height of the light on the other side of the room. He realized that the height he would find on the other side of the room would be slightly lower than the source of the light. Why? Because the floor of the room would be rushing upwards at ever faster speeds as the light was propagating across the room. Since the room was accelerating upwards at 9.8 meters per second, the light beam would appear to curve downward. However, if you were on Earth and you measured the two heights, you may think that there should be no difference. The light should go straight to the other side of the room. This appears to be common sense. But Einstein thought this can't be because it would violate the principle of equivalence. Acceleration of the room on a spaceship should be no different than the room under the influence of gravity on Earth. He realized that this meant light must bend in the presence of a gravitational field. But how could this be? Because light always takes the shortest path between 2 points. It should be going straight. Then he realized, wait a minute, maybe the light is taking the shortest path between 2 points. Maybe the shortest path is not a straight line. He imagined the curved surface of the Earth. The shortest path between any two distant points on Earth, if you're restricted to the surface of the Earth, is never a straight line because you have to traverse the curvature of Earth. So the shortest path is always curved. So maybe gravity somehow causes a curvature of space itself. He hypothesized that in space, perhaps a straight line is not the shortest path between 2 points, and that perhaps in the presence of mass and energy, space somehow becomes curved, so that the shortest path the light can take is a curved path. This was the key insight that Einstein had about gravity. But in order to express this mathematically, it required very complicated mathematics that even a genius like Einstein could not easily figure out. He contacted an old buddy of his from college days, mathematician Marcel Grossman. Grossman had just finished his PhD dissertation on the topic of, wouldn't you know it, the geometry of curved space is called Riemannian geometry. With his help, Einstein figured out the mathematics of curved space-time, and this curved geometry is really the basis of general relativity. Now you have to realize how different this was than the status quo of the time, which was Newtonian space and time, which presumed that time was fixed, space was fixed, and gravity was a mysterious force that could act at a distance from one massive object to another without touching it. In this model, gravity did not affect the underlying space and time, but acted within it. Einstein's theory was now that gravity was not a force between massive objects, but something that emerges from the interaction of space and massive objects. John Wheeler would later summarize the theory in 12 short words. Space-time tells matter how to move, and matter tells space-time how to curve. That's it. That's general relativity in a nutshell. And orbits of planets could now be explained not by some mysterious force that acts at a distance, but rather an interaction that takes place locally with mass or energy and the space around it. And this can be visually represented by the kind of graphic you see here to show how massive objects like planets form orbits around other massive objects. It's important to note that the trampoline analogy you normally see on TV shows and YouTube videos like this is a 2D plane used for visualization purposes only. The interaction occurs obviously in 3 dimensions, not just 2. It looks more like this graphic. Now this is much more difficult to visualize and animate, so it's typically not used, but it is more accurate. However, in order for this theory to really be taken seriously, it had to make a prediction that could be tested, and that prediction could not be explained in any other way. This test came in the form of Mercury. Mercury's orbit had been a mystery for decades because it was unusual. All planets orbited the Sun in an ellipse. The planet closest to the Sun, Mercury, also orbited in an ellipse, but it did something weird. It had something called a precession. What this means is that its ellipse never closes. The point of the orbit that was farthest from the Sun advances a little bit every time Mercury goes around the Sun. It's as if the ellipse itself is orbiting the Sun. No one could ever figure this out using Newton's equations. When Einstein applied his new curved space theory to this orbit, the new theory predicted exactly the precession that Mercury actually has. Finally, a theory perfectly matched the observation which had been a mystery for decades. You can only imagine how Einstein felt when he figured this out. There was a time when Einstein was the only person in the world who realized that the universe actually works this way. But many skeptics still remained. Many scientists still had doubts about Einstein's theory. But the most foolproof confirmation of his theory came 4 years after he published it. That's when a team led by English astronomer Arthur Eddington in 1919 photographed stars near the Sun during a total solar eclipse. If Einstein was right, then the position of the stars near the Sun would appear different than their predicted locations based on where they should be as seen at night. This would happen because as light passed near the Sun, it should be bent by the curvature of space due to gravity. And that's exactly what he found, confirming that the theory was correct. And this is the moment that Einstein became a celebrity. You might ask, okay, I get it. I get space curvature, but it's called space-time. How does time enter into the picture? Why is this not just a distortion of space, but also of time? This is where Einstein's first theory, special relativity, comes in. The essential presumption in special relativity is that light always moves at the same speed, regardless of perspective or reference frame. This means that light will have the same speed in an accelerating reference frame as it will in a resting reference frame. If this is the case, then it means that the speed of light in the presence of gravity will be the same as its speed in empty space. Speed equals distance over time, s equals d over t. But since the distance traveled by the beam of light in a gravitational field is longer due to the curvature of space, in order for the speed of light to remain constant, time itself must pass slower in the gravitational field relative to time in empty space. In other words, time increases proportionately with the curvature of space near the gravitational field compared to empty space to keep the speed of light constant in both reference frames. This is why time is considered distorted by gravity along with space. It is really just part of the same fabric called space-time. This has some massive implications. It implies that the observer experiencing no gravity at all sees the clock in a gravitational field running slower. This means that the clocks on Earth are slightly slower than the clocks on the International Space Station. This effect has been confirmed by many experiments and is taken into account in order to keep the clocks of the GPS satellites in sync with the clocks on Earth. Otherwise, your GPS apps like Google Maps would give you inaccurate locations.